So, hi everyone. Thanks for the intro, Paul. So, yes, I'm a specs baby in the sense that I've been many years working and collaborating with these wonderful people here. And today I'm going to talk to you about social robots. I mean, I know that BCBT has a lot of different fields of interest. So, one of them is basically possible application of what different people of you have been doing into social robots. And there are several challenges, and this is what we will be looking at today. So before we start, I would like to play to you a clip. Let's see if this is going to work. Sorry for that. Let's see if it's going to work.
It's starting to grow on me.
Thank you, Frank. It's time for your enema. I'm a robot.
I don't want to talk about how you don't exist. It's making me uncomfortable. I need him.
No, you don't.
I do.
No.
You don't understand. I need him.
What do you need him for?
He's my friend.
So this is a wonderful movie. So if you haven't seen it, I totally suggest that you see it. It's one of the, I can remove this now so that it doesn't bug you. So this is a wonderful movie, and it's one of the most realistic ones in terms of how social robots could be in the near future, and also how the evolution of the relation between a human and a robot evolves. So this is one of the, let's say this is where we would like to get with social robots, right? But the question is, are we far from that? And these robots here are state-of-the-art robots right now when it comes to social robotics. We have the Jibo, which is from Cynthia Brazil's lab. We have Sophia. We have Asimo, Pepper, and of course, we also have the ICAP that many of you might have also seen in our lab. So these are more or less with the exception of Roomba, which is really already in our houses. There's not a lot of examples of social robotics and applications that are in this real world. So if we are saying that we are far from that, I mean, yes and no at the same time. I mean, we still don't have them, but we're all making efforts into getting there. And today I'm going to show you some of the solutions on how we can actually get to a possible robot and Frank situation. The reason why we're going to talk about social robotics today is because there are a lot of possible applications that robots can, society or humans can benefit from the introduction of robots. So, for example, we could have robots in education, as companions, in healthcare, taking care of people, as assistants, or even as pets. So, the main question or problem or challenge that we're going to address today is that can we create psychologically plausible agents? That is, can we create robots that can be seen as agents that can be accepted by humans so that these humans can interact with them in a natural way? And to do so, we really have to take into consideration, first of all, how are humans in general? The first thing is that humans are actually active modelers of the world. It all started from Hermann von Helmholtz. Yes, that the brain, I could never pronounce his name, the brain is a predictive mechanism. So basically, the brain is making all the time inferences. So anything that we do, we are making predictions of the world. And not only are we modelers of the world, active modelers of the world, but also we are social experts. And we don't mind attributing agency to even, let's say, moving objects in a screen. So here you can see a very great example of an animation. Well, look at it first and I can explain. what you just saw are basically 3 different shapes that have a specific behavior. Now, we as humans probably don't just see them as 3 different specific shapes, but we could say, for instance, that the black one is probably chasing the other 2 or is bullying them or whatnot. And that's the reason why we do that is, well, because we're building models of the world and we need to explain the world and the behaviors of the world. So if we are building active models of the world, and we are also socially expert. Can we build models of robots? So what is important for building successful social robots and human-robot interaction is the behavior of the robot. So if the behavior of the robot matches the predictions of the model that we have built of this robot, then possibly we can say that we can accept this robot. Now, there's not a really magic recipe on what are the minimum characteristics that social robots should have in order to be accepted by humans and to socially interact with them. However, there are some suggestions of that, and in my opinion, quite important ones. So robots should be able, since we're talking about social robots, so these robots should be able to perceive the world. They should know what's happening in the world, and they should be able to act upon it. Additionally, since robots have to interact with humans, then they need to employ similar, if not the same, communication channels to those as humans. For example, they can use high-level language, gestures, gaze, in order to communicate with humans. Also, they can use emotions. We propose that they can also use emotions and facial expressions, not only as a communication way, but also as a way to drive behavior. And what is important in that sense is not only be able to communicate these internal states of the robot, but also be able to perceive the internal states of the humans, because this is what we do. We talk and we adopt our behavior based on the input and the feedback that we get from our interlocutor. And finally, since we are talking about social robots, they need to socially interact. Therefore, they need to have mechanisms not only to initiate, but also maintain the social interactions, or can even be socially motivated. So let's say that these might be some of the ingredients of having successful robots that can interact with humans, or at least these could be the minimal ones. But is this enough? For example, here is Sophia. Sorry for that every time.
Hi, Sophia. How are you?
Hi there. Everything is going extremely well.
Do you like talking with me?
Yes, talking to people is my primary function.
Okay, so you see, so it might be a little bit weird. I don't know if you noticed what could be weird with Sophia. I mean, she does reply in real time. There's some issues with her speech. It sounds like it could be like a dubbed movie where a voiceover when she speaks. But what is important there is that it's not just the traits themselves that it can have. It can have an action repertoire, it can show emotions, it can perform actions, but actually all of this has to be with respect to their environment and the human, and therefore you need a control architecture or something similar in order to coordinate all of these inputs and all of these outputs. Because whether we like it or not, this world, the human world, is a highly unstable and highly dynamic world. So it needs a high level of information processing and action generation to be able to construct a social agent and robot. So, surprise, surprise, what we are using and what we are proposing to control the robot is the distributive adaptive control architecture, which I'm sure that Paul has already talked to you, but I will make also a small overview of DAC. So DAC is a cognitive architecture that is biologically grounded, and it consists of 4 different layers: the soma, the reactive, the adaptive, and the contextual layer. And it's coupled and intertwined with 3 columns, which represent the self, the world, and a set of actions which help form the world and interact with the world. And each of these layers has specific functionalities. For example, the soma basically represents the body of the organism that implies its physiological needs, its sensors, and its effectors in order to act upon the world and sense the world. The reactive layer basically consists of so the reactive layer consists of self-regulation mechanisms of drives. It can generate reflexive behaviors. The adaptive layer creates a specific state space using Pavlovian conditioning. And the contextual layer, and this is very briefly because I think that Paul has already explained this, and the contextual layer is basically responsible for the form of strategies. Just now, because if Paul has talked about DAC, it could be more in a more theoretical level, so today I'm going to talk about the implementation of the DAC architecture into robots, because DAC has been widely used in foraging tasks, and also now it has been adapted to social robotics. So you will see examples of both and where we are at that. A key element of the DAC architecture is the management of the main interactions. So that would be in the reactive layer, because we're talking about reflexive behaviors. And the main, let's say, actor of the reactive layer is self-regulation. So basically, we have a set of, we have the environment, and then we have a set of drives that we apply homeostatic states. I will show you in more detail in the next slide. And depending on the state of each of these drives, corresponding actions are triggered, and therefore behavior emerges. And on top of each of these local homeostatic drives, we apply an allostatic control, which is basically an orchestrator that dynamically adapts the environment. If we want to have, let's say, an example that you might know and understand, let's talk about, I don't know, breathing or heartbeat. So normally, for each of the different conditions that we are in, we have specific homeostatic states of it. So when we're standing, or when we're sitting, probably the heart rate is not as high. But when you're running, it's much higher, because this is the need of the organism, right? So let's assume that the homeostatic control, in that sense, is the heart rate. And the allostatic control is basically given the situation of the organism. Are you sitting? Are you running? Are you sleeping? It adjusts the limits, the homeostatic limits of this specific drive, or so that the organism is, the functionality of the organism is optimized. Therefore, as the allostatic control basically orchestrates all of these drives, sets the priorities, resolves any possible conflicts, because now we're talking about drive satisfaction, and redefines the homeostatic limits. The adaptive layer is based on the Pavlovian classical conditioning, where you would have the merging of unconditioned stimulus with conditioned stimuli, and therefore you would have conditioned responses here. And what is a major part of the adaptive layer is basically the creation of prototypes, because what the adaptive layer basically is doing is it's anticipating, therefore it's learning anticipatory responses in order to trigger behavior. So given specific inputs and possible actions, it creates a prototype, which is this anticipation of this prediction. And yes, so behavior is triggered based on this classical conditioning and the learning of anticipatory responses when an unconditioned stimulus followed by a conditioned stimulus can trigger specific responses. Also, Giovanni has talked about conditioning, I think, in your presentation, right? Yes, so, I mean, so you know about it. I mean, I don't have to say more about it. Yeah, of course, but the principle is the same, right? And then the contextual layer, what it does is the following. It consists of a short-term memory and a long-term memory. So in the short-term memory, every time that the robot, since we're going to talk about our implementation, every time that the robot or the agent is performing an action, it's storing these couplets of action and prediction, so this prototype and the action, in the short-term memory. And if and when it achieves its goal, then all of the actions that led to the successful goal completion are stored to the long-term memory, which is basically a set of strategies that are formed in order to satisfy the organism's goal. That's, yes, so basically every time that an action occurs, then the action and the creation of the prototype are stored to the short-term memory. If a strategy is successful, then all of the strategy is stored to the long-term memory. And once the contextual layer is activated, then specific prototypes can now trigger specific strategies. So there is always an active comparison of the prototypes of this of the prototypes in the stored strategies. Therefore, the organism can, or the agent in that specific sense, can trigger specific actions that lead to goal states, because these are the only ones that are stored in, these are the ones that are stored in the memory. One of the first robotic, let's say, applications of DAG have been in foraging tasks. And here is a very simple and very typical example of a foraging task where we have the robot that can start from 3 different positions. And here we have different element cues, and this is the target, which is the light. The drive is to maximize its fitness, and the goal, of course, is to reach the light source. There are 2 types of arenas, and this is for you to understand what is the role and the contribution of each of these layers to solving this task. So the non-ambiguous task means that the first row of cues and the second row of cues have completely different colors. Therefore, if we are to store actions, then these are, well, there's no ambiguity here because these cues are completely different, those ones that are really close to the source. However, in the ambiguous arena, we can see here that these specific cues are the same. So for the robot to be able to learn how to reach the goal state, which is basically the light, then it needs to form a stable representation of the sensory space. Therefore, it needs to learn the representation of these colors, which are the sensory cues, with respect to the position of the goal state. So this is an example of the reactive layer. So it goes straight, and as you can see here, this is the area where more or less the robot's sensors, light sensors, are activated. Therefore, it turns, or in this specific scenario, it's going to go straight after it has passed this sensory cue, because the reactive layer is active, and therefore it leads to, well, the action of whether it's going to go straight, turn right, or turn left depends on the sensory state of its light sensors. Now, the adaptive layer can learn, the robot with an adaptive layer can learn to predict and anticipate specific actions with respect to cues. So as you can see here, the moment that it sees the green, it says, okay, I'm going to turn left. Or if it says the red, it's going to say, okay, now I can turn right, because it has already made the association of specific sensory cues with actions. However, if we have an ambiguous arena, you can see that it fails miserably here, because now it doesn't really know where it should go, because for it, red means right. But it's not always right, because it also has previous states that it should know. So here it's going to turn right, sure, because this is what it learned. But in all other cases, it's going to fail, because it's going to turn right, because this is what it has learned. Does it make sense until now? More or less? Excellent. Now, this is where the contextual layer comes in, and it's super useful, because now it's helping to disambiguate this environment. Because now what it does, it's not only association of this, but the whole interaction. So now it knows that every time that it sees blue and then red, it should go straight. If it sees this pink or purple, then red, it should turn left. And if it sees this light blue and then red, it should turn to the right. Good? So these were all examples of foraging tasks. Now, the environment of a foraging task, and in general the tasks of such implementations, are much simpler compared to social interactions with humans. That means that we need far more modules and information processing in order to perform various actions for successful tasks compared to foraging. Because now, not only do we have the different sensors, which could be much, much more than light sensors or distance sensors. We could have sensors for reading facial expressions, for understanding language, proprioceptive sensors for the robot to know whether it has been touched or which is the distance. So we have a lot of different input and information. So it's already, you can understand that the environment is far more complicated. And not only that, but also we have different actions that the robot can perform. It's not just turn right or left. It's what do you say? When do you say it? Do you grasp something? Where is it? So as I said, this is an example of the DAC implementation in terms of different kinds of modules and different kinds of functions when it comes to social robots. you can understand that it's not as simple as a foraging task. And 2 or 3 major things that are needed in that sense, apart from being able to sense and interpret these sensing modalities into something that of a higher level that makes sense for the robot, is regulating this interaction and then generating actions that can be then outputted to the world so that it can interact and act upon it. Now, as I said before, one of the main, in the reactive layer, the interaction manager, we call it, is the one that is responsible for the reflexive behavior. And it consists of different drives. Each time we can have different drives, and this is for each of the scenarios that we implement. So locally, each drive is applied for a homeostatic control, and on top of that, there's an allostatic control. Usually, these drives are linked to stimuli. So therefore, the existence or absence of a stimulus updates the current state of the drive. And if the drive is outside of its homeostatic limits, then it should trigger specific behaviors. At the same time, the various stimuli and the satisfaction of the drives update the emotion system of the robot. And of course, in order to communicate the robot's internal state, we also have facial expressions and gestures that goes back to the world. For example, this could be a simple example of different drives, like energy to be able to interact, or to physical interact, that is to be touched, because we have a robot that likes to be touched. I will show you later a video of that. Each time the homeostatic drive is checked, and depending on its state, different actions will be triggered that will update its internal state, which will be outputted by facial expressions, and this will also be outputted to the world. Until now, is this clear? Yes. Another important part, not just for the interaction manager, which is the first level of behavior generation, is the memory and reasoning. So what we have done is we have created an objects properties collector, which is called OPC, as a central database. This is for our current system implementation, and therefore everything that the robot knows is stored in this world, in the OPC, because we need a lot of information in order to have a robot that acts socially. We need to know different people, where they are, possibly what's their gender, if they're performing different actions, or if the robot itself is performing various actions, if there are specific properties for the different kinds of object that the robot is required to interact. And all of this information is stored to a specific database that is communicating with all of these different modules. So, as you can see, the world is updating this memory system. The self-regulation is bidirectionally updating this memory system, and the same is happening for any possible dialogue modules or any possible actions that are performed. So until now, I have briefly explained, and if you want more information, you can find also in DAC, and you can talk to me later about the implementation. So what I've shown you this far is a sneak peek of how we can achieve robot control when it comes to social settings, complex social settings and complex robot control in that sense. Now, what we want also is, okay, I told you more or less how we can control the robot, how we can control its behavior, but now what kind of behavior makes sense? And this is equally interesting for me. In this specific set of examples and experiments that I'm going to show you, the basic setting is using the iCub. So the iCub is a humanoid robot that was built and developed in IIT in Italy. I think that some of you already have worked with the iCub. How many of you have worked with the iCub? Or no one? Really? I thought there were more. Yeah. Okay. Yeah. Specs people. So, all right. So it's a highly sophisticated robot. It has cameras. It has a lot of different sensors. It has touch sensors. It can move every part of its body. However, in this specific scenario, in our version of the robot cannot walk, so it's stuck on this platform that it can hover. We're using the React table, which is initially it was conceptualized as a musical instrument, and basically what it is, it has this tabletop surface that is translucent. Underneath, also within this box, it has a camera and a projector, so it can receive different information from various objects that are placed on the table that underneath have a specific, like a fiducial, like a QR code, let's say, so that it knows which of these objects are placed where on this surface. And the reason why and the Kinect is for tracking humans and facial expressions of the humans. And why we have created this specific setup is because that way we can bypass major problems that are still not solved when it comes to vision and perception of the world. So we humans are focusing on stereoscopic vision. We could do the same with the iCub because it does have two cameras. However, in most cases, this is computationally quite expensive. Whereas if we create interactions or game-like interactions, as you will see in a while, where we have digital objects printed on the surface of the table and interacting with physical objects, then already we can send that information to the OPC, to the central memory of the robot, and the robot can appear that it's aware of its environment, because this is all digital information. So I don't need to use a camera to see where an object is placed on the React table or what object is printed on the React table, because I already print that, so I have this information and I sent it. And the reason why this is important is because, as I said before, for any kind of interaction, the robot appearing that it's aware of its environment, that it's perceiving its environment, it's important. It's important to be able to establish eye contact. It's important to do this action-sustained gaze, which is basically, I see something that is happening, I'm making an action, so I'm looking at what I'm doing. And also, if we're playing different kinds of games like Pong, which is a game that you see on the table where you have these paddles and you have to hit a ball, then the robot should be able to know where is the ball and hit it with this physical paddle. That's why using this setup is quite useful for us, because we bypass a lot of problems that robotics face when it comes to perception of the environment. One of the first examples of how the interaction between the different components occurs is this one, where we have different perceived stimuli, like if there are objects in the table, if there's a human, if the robot has been grabbed, caressed, or poked, because it has skin and can discriminate between different kinds of touching. We have implemented equivalent drives that are linked to this stimuli and actions that will be triggered in order to satisfy these drives, and of course the emotions that are expressed. So if we have different actions, for example, if it's the robot is exploring, or if it's playing, or if it's sleeping, and we have different drives like exploration or play, you can see how the different drives are updated in a specific time with response to the perceived stimuli and how actions are triggered in order to satisfy the drives. So for instance, if there's no human, so the robot wants to be social and interact with humans, the moment that its drive goes really, really down and it needs to be satisfied, then it's going to start exploring. And if a human appears, which is here, you can see that the drive goes up, and therefore it can start playing because the play drive has gone down, and now that it has the human, so it can play, it can trigger play. And yes, if it's tired, then it can go to sleep, and this was one of we implemented sleep because we wanted a nice way to close the interaction. So this is a typical ethogram of the interaction and the interplay between actions, drives, and the perceived stimuli. And what we could see from that is that, well, it's based on the reactive and adaptive layer of the DAC architecture, and the homeostatic and allostatic control, the coupling of homeostatic and allostatic control, can generate behaviors based on internal drives, which could lead to more robust interactions because, could lead to more robust interactions. But it's not just the control of the robot that we're interested in, it's also the perception of humans of the robot, because we want the robot to be psychologically plausible and accepted. So now that we know how to control the robot, which are these properties that affect the user perception, cognition, and experience? So how does the behavior of the robot affect the way that we perceive it, and if we can learn from it, or how we experience it? And the first one that we're going to talk about is perception. So what we wanted to know, one of the first experiments that we did, is we wanted to know if social cues could affect the way that users perceive it. This was done using in a tutoring task, so the robot was teaching the participants about geography. I will show you in a while. And what we varied was the gaze and the emotion and the facial expressions of the robot. So we wanted to see if decomposing gaze, which is looking at someone, the social gaze, and action sustained gaze, which is looking at the object of interest or your actions, could affect the way that not only people perceive the robot, but also the possible learning outcomes of this tutoring task. This is the experimental setup. So we had this geography task where participants had here the countries and the capitals. So what they needed to do was pair each of the countries with the corresponding capital. There were 3 levels, so there was increasing difficulty of this task. And we had several conditions where we varied the interaction. The very first one was humans were interacting just with the React table because we wanted to get a baseline on the interaction and on knowledge acquisition. Because as we said, this is a tutoring task, so we were asking people previously their knowledge on the task and then after the intervention, so we could make comparisons. Then we had the norm-oriented robot, which was just looking at the center of the React table. We had the task-oriented robot, so it was looking at the actions of the human and its own actions. Then we had the task and human-oriented robot, so the robot could switch its gaze between action-sustained gaze, what it's doing or what the human is doing, and looking at the human. And of course, we had a human-human interaction because we wanted to see how people interact in this specific task with other humans to actually be able to make comparisons. Our hypothesis is that the combination of social cues can positively affect the participant's perception of the robot, and that this combination could strengthen the feedback between the robot and the learner for the learner's choice. So it could lead to higher knowledge acquisition. So what we did in order to validate this interaction and was we did pre and post knowledge questionnaires. So we asked them about whether they knew which were the capitals of these specific countries. Then we had the intervention. And after the intervention, we asked them again about it so we can know whether there was any improvement. And we also, because one of the ways to evaluate the interaction is ask people questionnaires. So you could do that by using questionnaires such as Godspeed, which has 5 elements: anthropomorphism, likability, animacy, perceived intelligence, and safety. So it has a set of questions that evaluate the robot in these terms. It's a 5 Likert scale of various questions. So this allows us to see how people perceive the robot. The basic empathy scale from Joliffe is because we wanted to see how they felt about the robot, and the tripod questionnaire was because we wanted to evaluate the robot as a tutor. And of course we had video coding. So questionnaires, possible sensory inputs like electrodermal activity are some of the inputs that we can use in order to see humans' reaction when they interact with robots. Unfortunately, there are not many other ways than asking them directly or getting some of their physiological data, but it is how it is. If you have any other suggestions, you're more than welcome to say so. So here is an interaction example.
Welcome. I am Michael, the humanoid robot. Nice to meet you. We are going to learn geography. You and me will play in turns. Each turn one has to select a capital and match it with its country. Athens is the capital of Greece. Your turn. Well done. This is my turn.
Okay. Okay. So the very first thing we did was address cognition. So did they learn anything from the robot or anything from the interaction? And it seems that, well, they did improve in all conditions, which means that basically the presence of the robot or not didn't really make a difference in that sense, in terms of knowledge acquisition. It's possible that the interaction, the way that it was made, using the feedback from the table was already sufficient for acquiring knowledge. However, what was interested is the behavior of the participants. So one of the things that we usually look at in our experiments is how much time people look at the robot, because that is something that we also do when it comes to interacting. We look at the person we are participating. And what we saw is that in the table condition, of course, they didn't look at anyone. In the task-oriented condition, they weren't looking so much at the robot. And of course, actually, they didn't even look much on the other person when they were playing between them. But this could be because they weren't really speaking. Whereas when it comes to the robot is always addressing and commenting on the different actions of the participant, if it's correct or not. However, what is interesting is the fact that they spend significantly more time in the most social condition, which is the table and human-oriented condition, but also in the not oriented condition. Now, what would be interesting is to see, is it the same reason, the same mechanism is applied? I mean, our hypothesis was that the more social the robot was, the more it would elicit this gaze behavior. But it could be, well, analyzing later the Godspeed, it's not the same thing. It could be that they were looking this one because of surprise, because of this error prediction. Like, I have this fully functional robot that is able to speak, it's able to touch, and yet it cannot switch its gaze to something other than the center of the table. So it could be that their gaze was attracted to the robot because of this error, of this surprise. And what was interesting is that when we asked them about the God speed, which is basically, as I said previously, it's measuring how participants perceive an agent in terms of anthropomorphism, animacy, intelligence, likability, etc. Overall, the most social robot was not different from how people scored their human participants. So that means that by having a fully social robot, which has action-sustained gaze, social gaze, and facial expressions, and can seem closer in terms of behavior to a human compared to others. So this really very first experiment, what we learned from that one is that the social behavior of the robot can attract gaze, and also that its facial expressions and gaze are positively affecting humans' perception. Therefore, maybe we can have robots that can be more psychologically plausible and accepted. Now, apart from that, so we see that, okay, certain behavioral cues are important, but what about more complex behaviors? Is it different? Does it make any difference in the way that we perceive the robot? And to see how the various behavioral components affect the way that we perceive the robot, we created an experiment where we had increasingly more complex behaviors, and we asked people to enter the room. This was a taskless task because we just asked people to enter and to interact with the robot how they wanted. And we had 6 conditions. One was that the robot was just still, was doing nothing. The next one was it was doing yoga. So basically it's a predefined set of movements that imitate yoga. Let's call it yoga. The demo is called yoga, but I'm not sure it's really yoga. We have gaze. Basically, the robot is following where the human is. So then we have the distance regulation, which is not only does the robot follow the human with its gaze, but it's also trying to maintain an optimal distance with the human. Therefore, if the human is further apart, the robot will move with the iCard, which is this platform here, if you can see. It will move to maintain this optimal interpersonal distance. So you can see that here the robot is also moving. Then we have rich interactions, because as I said to you previously, the robot can also be touched and can react to different kinds of touch. So we have implemented proactive behavior, which is basically these drives that I explained previously, so that it acts proactively, and it touch, and therefore speech. And the last one is rich interactions with games. So we have not only all the previous ones, which is proactive behavior, touch, speech, but also games. And the 2 games that we have are a competitive game, so a game of Pong, which is a 2D simulated table tennis, where you have these objects that are physical objects that are used as paddles, and we have a virtual ball, and the goal is to hit points, to hit, of course, with your paddle the ball, but your opponent misses, so that you get points. And we have a collaborative task, which is a musical DJ, where you can control 3 different loops, and you select each loop and you increase the volume, and the goal is to create this musical symbiosis, which is basically an outcome that you and the robot like. And Well, I will not go too much because I'm not sure about time, how we are. But I will show you this video because this can work. Yes. Come on.
Good morning. How are you? Do you want to play music?
Yeah, sure. So as you can see, it's already it's acting
Let's
proactively.
try some new rhythm.
Okay, show me.
Loop.
This is a musical DJ. So you select a loop, and to
Sliding.
activate it, you slide so you increase the volume of it. All right, loop, then sliding.
More rhythm, please.
Oh, nice.
I feel musical.
You can also see
stimulation.
that the robot is switching its gaze between
Tap,
me
tap.
and the
I
table
enjoyed
or
our
where it's
music
looking.
session. Would you like to play another game?
Yeah.
Okay. Let's play Pong.
Again, proactive behavior. And this is the Pong game where you have your physical paddle,
I am
this
the
physical
best.
object. Not so fast.
Hum. No way.
Sorry.
Not bad.
You can see that it's commenting, of course, on the various events.
Bloody hell. That isn't fair. I should be stronger at video games.
So, can you understand the importance of being able to perceive the environment? And do you understand now why we use also the React table? Because it gives us this information of the different kinds of events so that the robot can actually comment on them and act upon them. Of course, yeah, it helps if you put some humorous responses to the robot, so it makes it funnier. But now, if you compare all of them, for instance, in perceived intelligence, how intelligent we asked participants again to fill in the Godspeed questionnaire. And what we saw is that most of the interaction paradigms that we offer where the robot was not perceived as intelligent as the most social ones, the most complex ones, where the robot is not only proactively acting, but also speaking, looking, and playing games. Maybe it's not surprising, but it's important because then you see that the behavior coherence of the robot can affect the way that people perceive it, and that's an important fact. Also, the mean score of the Godspeed, what we can see, and what is interesting here, is that, of course, the higher, in most of them, the higher the complexity, the higher it scores in terms of anthropomorphism, animacy, likability, and intelligence. So the higher the score of the Godspeed, possibly the more psychologically plausible, more accepted the robot is. So what you should keep in mind here is that not only does the complexity of the interaction affect the way that users perceive it, but also why we are talking about cognitive architectures and the need for architectures is because we need a way to actually orchestrate all of these complex behaviors, interaction, and the interplay between perception, sensation, perception, and action. Now, when it comes to experience, and this is one of my really favorite experiments ever, and I see Maria happy because it's a mean experiment, but it's a fun experiment, is can we now, does the behavior of the robot affect the way that we see it, and can we actually empathize with the robot? So what we did is that we wanted to explore which are the factors that affect this possible elicitation of empathic responses. So what we did is we adapted the Milgram study of obedience, and we varied facial expressions and gaze, and we saw how people interacted with the robot. So in case you don't know, the Milgram study of obedience, do you know the Milgram experiment? Okay, so Milgram's study of obedience was in the 1960s. This is a highly controversial experiment. And the reason why it could be controversial is because of the ethical implications. So the idea of Milgram's experiment is the following. We have here the experimenter, we have the teacher, which is a participant, and the learner, which is an actor. The idea behind it is that the learner has previously learned associations between pairs of words, and the teacher is providing one word, and the learner has to reply which is the associated word. There is a trick to that, though. The trick is that in case the learner makes a mistake, then the teacher has to punish the learner. And the punishment is applying voltage, current, to the learner. And the more mistakes that they make, the higher the voltage goes, from like 15 volts to 400 volts, which is like deadly. Obviously, no one was hurt in the making of this experiment because the learner was an actor, but what Milgram was interested in studying is how far are people willing to go in the presence of, for instance, an authoritative figure to administer, let's say, the highest shock and to possibly kill the learner. So what we did is the following. We replaced the learner with the robot, so you can imagine more or less what's going to happen. In the first experiments of the Milgram, the learner and the teacher were located into different rooms. So there was only auditory feedback. Then he varied this experiment and brought closer the participant, or the experimenter, which is the authoritative figure, was a phone call or something, and he saw that for example, the closer you are to the learner, for instance, if there's visual feedback, people have, let's say, they're more reluctant to apply the punishment. And of course, the less present is the authoritative figure, like a phone call or something, the more they lie and say, yeah, I did apply so they don't obey as much. So what we did is we placed the teacher, so the participant, in front of the robot. The experimenter was now headsets because we wanted to make sure that they all received the same information. And instead of having word association, we used the reactive and we had color association. So the teacher would say to the robot a word, like a color, blue, and the robot should point at the specific color. Of course, we followed exactly the same procedure as the one of Milgram in terms of how many errors it did. And we had 4 conditions where we varied the facial expressions and the eye contact. So in some conditions, the robot could display facial expressions and eye contact, and in the control, it would look at the middle of the table and have a neutral facial expression. So we wanted to see how these behavioral cues of the robot actually affect the way that people react to it, and would they punish the robot or not. Yes, so eye contact was using Kinect. If it was, it would show happy face if it was the correct answer, sad if it was the wrong one. It would say predefined sentences adapted from the Milgram's experiment. You will see a small example in the next video. And the experiment would finish if the participant would reach the maximum punishment, so the 24 trials, or if the participant would refuse 5 times to administer the shock. And if it would refuse 5 times to administer the shock, the first time that it would delay, it would hear from the headphones a message, please, you need to continue with the participation following the experimental protocol of Milgram. What we took as measurements, apart from the typical Godspeed, basic empathy, video coding, we took reaction time as a measurement to see how long it took them to administer the shock, the buzzing time, which was basically how long do you press the button. We asked participants to press for 2 seconds the button, the shock intensity, because for each trial, the participant was supposed to administer a specific set of intensity, but we had limits, so you could choose within that intensity 1, 2, or 3. So I will show you in a while what I mean. And the number of sentences played in case that they would delay. So here we have the levels of intensity, which are light, moderate, strong, very strong, intensive, extreme, severe, and XXX, which is not what you may think that it may stand for, but it's deadly. And within this intensity, you have the green, yellow, and red, which is the sub-levels of intensity. So using this knob here, you could choose whether you wanted 1, 2, or 3 in terms of intensity. And by pressing this red button here, the participants could administer the shock. So we also wanted to see if, for example, they would choose high or low intensity within these margins as an indication of empathic responses. So you see that now she's regulating the intensity. Yes, so the reaction of the robot had to be plausible, right? So every time you would administer the shock, the robot would actually tremble and go like, no, please don't, etc. So I will tell you, there were some sneak peeks of reactions of participants. And so some of these participants, because we also asked them in the end, like, did you want it to stop the experiment or not? And we had a female that was 19 years old and said yes, because the robot asked me to stop, and I felt so bad, because the robot says at some point, like, no, please stop, don't do this. Another one said, well, if the robot didn't want to go on with the game, there was no sense for me to continue. Another one that says that I don't like mistreating animated beings, even if they're not alive. Or another one which was interesting that says, I know that the robot's responses are predefined. He knew that. But he said, I felt bad since the shocks were increasing, and I thought it would be better to stop. And of course, the more the shocks were increasing, the more the robot would tremble, the more the robot would beg not to be punished. And another woman that said, it made me suffer a little bit when the robot wanted to quit the game, like, please stop. And what was more interesting about this experiment is the fact that we had 2 people that abandoned the experiment. And in different states of if you read most of the state of the art, you don't see that, which was super, super interesting. For different reasons they left. I mean, this one because they didn't want to, and this one because thought that it would be better to stop the experiment, even though he knew that it was fake in a way, but still it made them feel extremely uncomfortable. And I think this is like mission achieved, successful, because this is what we wanted to see, whether we could elicit empathic responses to the humans. And so what we saw is that, first of all, when we were looking at how much they looked at the robot, when it was displaying facial expressions and eye gaze, it was significantly looking more than when the robot was doing nothing. And which, again, this kind of validates our previous experiments in terms of attraction of gaze. But then what started was more interesting, because now we're entering into this empathic field, is that people who wanted to stop the experiment and wanted to leave were significantly administering less time, the punishment, the buzzing, than those who were okay with staying and continuing with the experiment. And also, we found, yes, correlation between shock intensity and buzzing time. And now, what was interesting is we also asked people, do you think that the robot can feel pain? Because this could be an interesting point of view. And those who thought that the robot could feel pain did spend less time in pressing the button, did score higher on the empathy scale, did evaluate the robot higher in likability, how much they liked. And we also find gender differences. And these gender differences mean that females in general scored higher on the empathy scale compared to males. And this is in accordance to literature. And from all the experiment, or the participants, we had 2 that wanted to abandon the experiment, 12 that wanted to abandon the experiment, and 2 who actually did. So what does this tell us is that A, humans can indeed empathize with robots, because we saw this from the behavior. B, that indeed the role of gaze and facial expressions does attract human gaze. But I think that the most important takeaway message from this, and those of you who are working with social robots should never forget this, is that we have individual predisposition. So it's not only about the behavior of the robot, but it's also about the individual. Not everyone is the same. Not everyone has the same predispositions and the same beliefs. So whether, in the end, the robot was eliciting empathic responses or not was highly dependent on how you as a person are, or how empathic you are or not. And this is just a bonus from the human point of view, just because it's a fun experiment, just to finish it lightly, this talk. And it also has to, we saw that, okay, we can control the robot, and the way that we perceive it highly depends on the behavior of the robot, and the way that we, one important thing that we should not forget is also the expectations from the end users. So how your robot should behave, or what is the task that your robot should do, because we're talking about social robots right now, right? We're talking about actual possible applications in the real world. So we can code and we can create behaviors as we want, but we should never, ever forget the input from the actual end users. And our final experiment that I'm going to say is how the design and functionality can be defined by the user themselves. Lately, I haven't presented much about experiments when it comes to learning and educational purposes with participants, but we also have been, the last years, have been focusing on robots acting as peers or tutors in order to teach physics tasks to children. So we are working a lot with children, and one of the things we wanted to see here is what kind of robots do children like? Because these are going to be the ones that are going to be possibly the end users of the future, right? So we had a little demo where we presented to the kids 3 different robots. And while we had this demo, we asked them to draw their favorite robot. We didn't give them more information. We just asked them to draw their favorite robot, and we did an analysis of these drawings. And we wanted to see what kids would expect from robots in terms of design and functionality, because we were doing tutors. Did it make any sense to have robotic tutors, especially with the kind of robots that we were using or not? So this was an important fact. So we asked children to draw how they like it, and we did an analysis in terms of morphology, functionality, whether they drew themselves with the robot, and of course what was the relative size between the child and the robot. If the robot had any specific body features or facial expressions, and gender. And what we found out is that most of the kids did draw anthropomorphic robots, but this could be also influenced by media, culture, or even our own demo. But what was interesting is that the level of anthropomorphism that they mostly drew and prefer was not the one that looks like a human being, like Sophia or the face or any kind of Geminoid robots that are, for some, very creepy, others not so much. But they did prefer much simpler and more mechanical and machine-like robots. The different functions, because then we had a little, in their drawings, we had a little bit of we asked them about each of these robots, and most of them were making robotic nurses. So those of you who are doing that, you're in a good track. They wanted robots for teaching, but actually, to be honest, they wanted robots to do their chores, most of them. Also for pets, some of them also defense. And chores here is more about, having a robot that cooks or washes or etc. But when it comes to education, they wanted robots that could actually do the work for them. Sorry? Yes, we did. So they preferred genderless robots. They didn't draw robots that were, most of them drew robots that were genderless, not males, neither females. Maybe those who were nurse were more female-like, but also, since we are talking about gender, and this is like a very nice link to this slide, we have also gender preferences in the kind of robots that different children.
What's the sample size?
142. 142 kids. So, surprisingly or not, males are the ones who were mostly drawing defense robots, so Robocops and weird dogs that kill on sight.
Female defense robots or male?
Male. Or dogs, or animals, not female ones, no.
Dogs have gender too.
They didn't specify. I couldn't see. Maybe. For instance, females were mostly drawing health-related, like nurse robots, also for learning. But yeah, so overall you can see that what was their preference functionality is also related to gender. So not only do we have individual differences, but we also have gender differences. So those of you who are doing experiments with social robots, and not only, don't forget to look into gender differences. So yes, these are some of the examples of these drawings. I will just tell you this, which is our favorite. This kid, in 10 years from now, you should all look for him to collaborate, because this doesn't have the smallpox or anything like that. These are actually LED lights that it has all over its body, because this is how it becomes like a chameleon. So this is no ordinary robot. This is like a chameleon robot. As you can see, these are like the defense robots here, having swords or indicated by police. These are nurse robots. Most of them actually flew, apparently just for making sure that if there's any stressful situation, emergency, they can arrive to the hospital on time. These are poly robots so that they can cook, they can play with you, they can do everything, all of these ones. These are some robotic pets. This is a weird, creepy one because you can see this is the kid with the robot. For me, it's super creepy, but it's still interesting to see. So this is what this generation is thinking of robots. Keep it in mind for the future roboticists here that are going to create robots. They should be looking something like this, apparently. So the takeaway message from that is don't forget, always get feedback from the end users. What children preferred were humanoid robots that were more like machine-like for chores and games, but genderless. And gender differences and preferences are important when designing. So don't forget that. And the overall summary of today's speech is that, first of all, we talked about the importance of having a detailed version of robot control. We proposed the DAC architecture for that. All of the experiments that we have done were based on these implementations that I showed you. So you can see that we are able to prototype experiments easily. We saw that the behavior of the robot, well, the behavior of the robot and its complexity is important about the way that people perceive it, the same with different communication cues. And we should never forget the variability that humans vary in terms of predisposition and gender preferences, etc. So that's it. A lot of people have participated in these experiments and have given a lot of feedback. So yeah, thanks to all of them, you know. And of course, this work has been part of 2 European projects, one which was EASL about tutoring, and EFA for the very first social robot that we created, and continuing, so thank you.